Okay, so picture this. You're lying on your back in a field somewhere. The sky is wide open above you, and you're thinking, man, the universe is so calm, so peaceful, so quiet. And yeah, from down here, it looks like that. But the truth is, the solar system you live inside is one of the most violent, bizarre, gut-punchingly weird places imaginable. And most of that chaos is happening in total silence right now, while you scroll your phone. That's the trick of space. It looks relaxing. It is absolutely not. If this kind of thing scratches your brain in the right way, do yourself a favor and hit subscribe. We post this stuff every single week. You can even smack that little bell if you're feeling brave. Cool? Cool. Let's drift. Let me start you somewhere far, like really far. The farthest planet we've got, Neptune. Neptune is the last real planet in the lineup, way out at the edge of everything, sitting in the cold and the dark about 4.5 billion kilometers from the sun. To give you a sense of how absurd that distance is, sunlight, which is the fastest thing there is, takes more than 4 hours just to crawl all the way out there. 4 hours. The same light that hits your eyeball in 8 minutes takes 4 full hours to even reach Neptune. So you'd think a planet that far from the sun, that starved of warmth, that frozen and forgotten, would just be sitting there quietly, doing nothing. Basically a giant blue ice cube, minding its own business. Yeah, about that. Neptune has the fastest winds in the entire solar system. Not the fastest winds among the cold planets. Not the fastest winds for its size. The fastest winds anywhere we've measured. Full stop. We're talking about gusts ripping through that atmosphere at over 2,000 kilometers an hour. Let me make that real for you. That is faster than the speed of sound here on Earth. If you somehow stood on a platform in Neptune's upper clouds and you shouted, the wind would carry your voice away before the sound itself could even break loose. The storms there move faster than your own words. And here's the part that breaks your brain. That doesn't make sense. It shouldn't be possible. Wind needs energy. Storms need fuel. On Earth, our weather is powered by the sun pumping heat into the atmosphere, churning everything up, driving the whole machine. That's why hurricanes form over warm ocean water and not over a frozen lake. But Neptune is so far out that it gets barely a whisper of sunlight, something like 1,000 times less energy from the sun than we get here. By every rule we understand, Neptune should be calm. It should be dead quiet. Instead, it's screaming. So scientists are still kind of scratching their heads about where all that energy is coming from. One leading idea is that Neptune is generating its own internal heat, radiating out more energy than it actually receives from the sun, basically running its own furnace deep inside. And that internal warmth, combined with the lack of any solid surface to create friction and slow the wind down, lets the storms accelerate to these insane supersonic speeds with almost nothing to stop them. On Earth, mountains and oceans and land masses drag on the wind and bleed off its power. On Neptune, there's nothing to grab, so the wind just goes and goes and goes. And when you actually saw it, when the Voyager spacecraft flew past Neptune back in 1989 and sent the pictures home, there it was. A massive dark storm sitting in the southern hemisphere. A swirling oval the size of the entire Earth, churning through that blue atmosphere. They called it the Great Dark Spot, a storm wide enough to swallow our whole planet, blowing faster than sound, out in the freezing dark where nothing should be moving at all. And here's the crazy part. By the time we looked again, with the Hubble telescope a few years later, the Great Dark Spot was gone, just vanished. And then new dark spots appeared elsewhere. That's how alive and restless that atmosphere is. These continent-swallowing, sound-beating superstorms form, rage, and disappear. And the whole thing is happening right now, this very second, in total silence, 4 hours of light away, on the farthest planet from your home. So yeah, the peaceful blue dot at the edge of the solar system. It's basically a frozen hurricane factory that runs on a fire we don't fully understand. Relaxing, right? Now, while we're hanging out way at the cold end of things, let me tell you about something that happens inside Neptune, and inside its neighbor, Uranus. Because this one sounds made up. It sounds like something a kid would invent. But the science behind it is real, and it's one of the wildest ideas in planetary chemistry. It rains diamonds. Let me explain, because you would be right to call me crazy. You'd hear that and think, sure, buddy, diamonds falling from the sky. What's next? Gold, snow. Well, you're not alone in being skeptical, but unfortunately for your skepticism, you're wrong. Because the physics here is shockingly solid. Here's the setup. Uranus and Neptune are what we call ice giants. They're not made of rock like Earth, and they're not mostly hydrogen and helium like Jupiter and Saturn. Instead, a huge chunk of what they're made of is a thick, slushy, hot soup of water, ammonia, and methane. And methane is the key ingredient here, because methane is a molecule built out of carbon and hydrogen. One carbon atom holding hands with 4 hydrogen atoms. That carbon is the seed of the whole thing. Now think about what it's like deep inside one of these planets. As you sink down through the atmosphere toward the core, the pressure climbs to absolutely monstrous levels. We're talking millions of times the air pressure you feel at sea level. The temperature shoots up into the thousands of degrees. It is a crushing, scalding, hellish environment down there. And under that kind of insane pressure, something remarkable happens to the methane. The molecules get torn apart. The bonds holding that carbon to its hydrogen just can't survive, and the carbon gets ripped free. And once you've got loose carbon, squeezed under millions of atmospheres of pressure, baking at thousands of degrees, you know what carbon does in those exact conditions. It crystallizes. It packs itself into the hardest, densest arrangement it can find. It becomes diamond. So deep inside Uranus and Neptune, the theory goes, that carbon clumps together into actual solid diamonds. And because diamond is heavier than the slushy soup around it, those diamonds start to sink. They fall. They drift down through the dense interior toward the core, slowly raining through the guts of the planet, a steady, glittering downpour of precious stones falling through the dark. And I want you to sit with that for a second. Right now, as you're listening to this, billions of kilometers away, there are diamonds falling like rain inside 2 planets. Not a metaphor, not poetic language. Carbon, crushed into gemstones, drizzling down toward planetary cores in the cold and the dark. Now you might ask, is this actually true, or is it just a clever idea on paper? And that's the best part. Scientists actually recreated it. In laboratories, researchers took plastic, which is full of those same carbon and hydrogen building blocks, and they blasted it with powerful lasers to generate shock waves, briefly slamming it with the kind of extreme pressure and temperature you'd find inside an ice giant. And in those fractions of a second, they watched tiny nanodiamonds form right there in the experiment. They made it happen. They proved the recipe works. So it's not just a fantasy. The conditions are real, the chemistry is real, and the diamond rain is very likely real. Some estimates even suggest these diamonds could grow surprisingly large as they fall and merge, possibly forming massive gemstones deep down, maybe even settling into a layer of diamond around the core, a literal diamond shell hidden in the heart of a planet. And that's why I love this one so much. Because from the outside, Uranus and Neptune just look like calm, pale, featureless balls floating in the dark. Soft blue, soft teal, nothing dramatic to see. But the inside is a pressure cooker, tearing molecules apart and forging treasure out of the wreckage. Quiet on the surface, violent underneath. That's the whole theme of this place, and we're just getting started. Now, let's leave the cold edge and come back toward the sun, all the way in, to a planet that's basically Earth's evil twin, Venus. Venus is the second planet from the sun, and on paper it should be the planet most like home. It's almost exactly the same size as Earth, nearly the same mass, made of the same kind of rock, sitting relatively close to us in the lineup. For a long time, before we knew better, people imagined Venus as a warm, tropical jungle world hiding under its clouds, a lush sister planet. People genuinely thought it might be paradise. It is not paradise. Venus is one of the most hostile places in the solar system. The surface temperature is hot enough to melt lead. The air is a thick, crushing blanket of carbon dioxide, so heavy that standing on the surface would feel like being almost a kilometer underwater on Earth. And it rains sulfuric acid in the upper clouds, so scratch the jungle idea. Venus is a furnace wrapped in poison. But that's not even the weird part. The weird part, the part that genuinely messes with your sense of how planets are supposed to work, is the way Venus spins. Every planet in the solar system spins. That spin is what gives you day and night, the rotation turning a place toward the sun and then away from it. Earth spins, and one full turn takes 24 hours, which is why a day is a day. And almost every planet spins in the same general direction, the same way they orbit the sun, because that's how they all formed together out of the same spinning cloud of material billions of years ago. It's the natural inheritance of how the whole system was born. Venus didn't get the memo. Venus spins backward, seriously. While almost everything else in the solar system turns one way, Venus turns the opposite way. It rotates in reverse. And what that means, if you could somehow stand on the surface and watch through that thick atmosphere, is that the sun would rise in the west and set in the east. The complete opposite of everything you've ever known. Sunrise in the wrong direction. The sky running backward. And it gets stranger, because Venus doesn't just spin backward. It spins absurdly, ridiculously slowly. It is the slowest spinning planet there is, by a huge margin. It takes Venus about 243 Earth days to complete a single full rotation. 243 days for one turn. One Venusian day, one single rotation, drags on for the better part of an Earth year. And here is the fact that flat out breaks people's brains. Venus takes about 225 Earth days to go all the way around the sun once. That's its year. So do the math with me. The day, the time it takes to spin once, is 243 Earth days. The year, the time it takes to orbit the sun once, is 225 Earth days, which means a day on Venus is longer than a year on Venus. The planet finishes its entire trip around the sun before it even manages to finish a single spin. Your birthday would come around before the sun has come up and gone down once. Let that sink in. On Venus, you could live for years, plural, and not see a full day pass. So how on earth does a planet end up spinning backward and slower than its own year? And the honest answer is, scientists aren't 100% sure, which I think is great, because it means there's still a mystery sitting right next door. There are a couple of leading theories. One idea is that a colossal impact early in the planet's history, a giant collision with another huge object, slammed into Venus hard enough to flip it or knock its spin into reverse. Another idea, and this one's pretty elegant, is that over billions of years, the sun's gravity tugging on Venus, combined with the friction and drag of that incredibly thick, heavy atmosphere, gradually slowed the planet's spin down, dragged it to a near stop, and eventually tipped it into turning the other way. A slow-motion tug-of-war between the sun and the air played out across the entire age of the solar system. Either way, the result is this genuinely alien world. Same size as Earth, same rock, born from the same cloud, and yet it's a backward, sweltering, acid-clouded place where the sun rises in the west and a single day outlasts the year. From a distance, Venus is the brightest, prettiest thing in your night sky, the evening star, gleaming white and serene. Up close, it's chaos in slow motion. Quiet violence again. You're starting to see the pattern. Okay, so now let me take you back out to maybe the most beautiful object in the entire sky, Saturn and its rings. If I asked you to picture a planet, just close your eyes and imagine one. There's a good chance you pictured Saturn, the big golden ball with that perfect, glorious set of rings wrapped around it. It's the postcard of the solar system. It's the planet on every textbook cover. Those rings are so iconic that they basically define what a planet is supposed to look like in our imagination, even though Saturn is actually the only planet with rings that dramatic and bright. And here's the thing about those rings. They look permanent. They look eternal. They look like they've always been there and always will be. This stable, gorgeous, unchanging crown. You assume they're as old as the planet itself. 4.5 billion years of glittering perfection. Nah, and this is where it gets sad and beautiful at the same time. Saturn's rings are dying. Right now, we are watching them disappear. Let me explain what's actually going on because it's wild. Those rings aren't solid. They're not a single smooth disk. They're made of countless chunks of ice and rock, ranging from tiny grains the size of dust, all the way up to boulders the size of houses, all orbiting Saturn in a vast, flat, swirling band. Mostly ice, bright, reflective water ice, which is exactly why they shine so beautifully and why they're so easy to see. But they're not just sitting there peacefully orbiting. They're leaking. Saturn's gravity, along with its magnetic field, is constantly pulling material out of the rings and dragging it down into the planet's atmosphere, where it falls in and burns up. Scientists actually have a name for this. They call it ring rain. The rings are raining down into the planet, a steady drizzle of ice and dust being pulled out of that beautiful band and swallowed by Saturn itself. And this isn't a tiny trickle. Measurements, including data from the Cassini spacecraft that spent years orbiting Saturn, suggest the rings are losing an enormous amount of material. Estimates from the ring rain alone suggest something like tons of it falling into Saturn every single second. Picture that, an entire swimming pool's worth of ring raining down into the planet over and over, constantly. The crown is melting. And here's the crazy part, the part that genuinely flips your sense of time upside down. Scientists now think the rings might be incredibly young, not billions of years old like the planet, maybe only a few 100 million years old, which sounds like a lot, but in cosmic terms it's nothing. It means the rings probably weren't there when life was first crawling around on Earth. It means that when dinosaurs were stomping across our planet, Saturn might have either had no rings at all, or rings that were just forming. The dinosaurs may have lived and died and looked up at a Saturn that didn't have its famous crown yet, or had a very different one. Think about that. Saturn's rings might be younger than the dinosaurs. The most iconic feature in the solar system might be a relatively recent temporary decoration, a blink, a phase the planet is going through. And because they're leaking away so fast, they won't last. Based on how quickly the ring rain is pulling material down, scientists estimate the rings could be largely gone in another few 100 million years, maybe less. Which means we, humanity, are living in an incredibly lucky, narrow window of time where Saturn has its rings, and we have the technology to see them, photograph them, fly spacecraft out to study them. A few 100 million years too early, no rings. A few 100 million years too late, no rings. But right now, in this exact slice of cosmic history, they're here, and we get to look at them. That, to me, is is the most quietly emotional fact in all of this. The thing you think is eternal is actually fleeting. The most permanent-looking feature in the sky is in the middle of vanishing, and it's happening so slowly that to us it looks frozen and perfect. But on the scale of the planet's life, those rings are slipping away like sand through fingers. Turns out even the most beautiful things up there are temporary. Now, speaking of things we almost didn't catch in time to see, let me tell you how we found Neptune in the first place. Because this is one of the greatest detective stories in the history of science, and it didn't happen with a telescope. It happened with a pencil and a piece of paper. Here's the situation. Back in the early 1800s, astronomers knew about Uranus. It had been discovered in 1781, and they'd been tracking it as it slowly crept along its orbit around the sun. And they had the math, Newton's laws of gravity, that could predict exactly where a planet should be at any given time, where it should appear in the sky on any given night. The math was rock solid. It worked perfectly for every other planet, but Uranus wouldn't cooperate. When astronomers carefully tracked Uranus and compared its actual position to where the math said it should be, it was off. Just a little. It would drift ahead of schedule, then lag behind, wobbling away from the predicted path. A tiny discrepancy, but a stubborn one that wouldn't go away no matter how carefully they checked their work. Now, when something like that happens, you've basically got two choices. Either the laws of gravity themselves are wrong, which would be earth-shattering, or there's something out there we can't see, some hidden mass, tugging on Uranus with its gravity and pulling it off course. Some unseen planet, lurking farther out in the dark, gently yanking on Uranus every time they passed near each other. And here's where it gets beautiful. A couple of mathematicians, working separately, decided to bet on the hidden planet. The most famous of them was a Frenchman named Urbain Le Verrier. And Le Verrier did something that still gives me chills. He took those tiny wobbles in Uranus's orbit, those little discrepancies, and he worked backward through the mathematics of gravity to figure out where an unseen planet would have to be to cause exactly those wobbles. Just from the numbers, just from the math. He calculated how massive this hidden world must be, and crucially, exactly where in the sky it should be sitting at that moment. Let that hit you for a second. He found a planet without ever looking through a telescope. He found it with logic and arithmetic. He pointed at a specific empty-looking patch of sky and basically said, there's a planet right there. Go look. And so they did. Le Verrier sent his prediction to an astronomer at the Berlin Observatory, a man named Johann Galle. And on the very night Galle received the letter, in September of 1846, he pointed the telescope to the exact spot Le Verrier had calculated. And there it was, Neptune. Sitting almost precisely where the math said it would be, within a degree of the prediction. They found it on the first night, basically the first try, because the calculation was that good. Think about how staggering that is. A new planet, a giant world billions of kilometers away, was discovered first on paper, predicted into existence by pure mathematics, and only then confirmed by an eyeball at a telescope. The universe behaved so reliably, so precisely, that a human being could sit at a desk, do the math, and tell the cosmos where it was hiding. And the cosmos said, "Yep, you got me." That's the moment a lot of people point to as one of the greatest triumphs of science ever. Not because of the telescope, but because it proved that the laws we'd worked out actually run the whole show, all the way out to the edge of the planets. The same gravity that pulls an apple off a branch was strong enough and consistent enough to reveal an invisible world from across the solar system. Neptune wasn't stumbled upon, it was summoned by equations, and I think that's a perfect example of the quiet power humming under all of this. The solar system looks like chaos, superstorms and backward worlds and rings melting away. But it all runs on these deep, reliable rules. Rules so dependable that a clever person with enough patience can predict a planet nobody had ever seen. Quiet order underneath the quiet violence. Now, let me bring you down to a place you might actually visit someday, if humans keep at it. Mars. And specifically, the single biggest mountain in the solar system, sitting right there on the Martian surface. Olympus Mons. When you think of a big mountain on Earth, you think of Everest. Everest is the giant, the ultimate, the roof of the world. Climbers train for years and risk their lives just to reach the top of it. It stands about 8.8 kilometers above sea level, almost 9 vertical kilometers of rock punching up into air so thin you can barely breathe. Everest is the biggest thing we've got, and it is genuinely massive by any human standard. Now throw all of that out, because Olympus Mons on Mars makes Everest look like a speed bump. Olympus Mons is a volcano, and it is nearly 3 times the height of Everest. We're talking about a mountain rising somewhere around 22 kilometers above the surrounding plains. 22 kilometers straight up. That's so tall its peak would poke right out of the top of Mars's atmosphere. If you were standing at the summit, you'd basically be standing at the edge of space, in air so thin it's practically a vacuum. But the height isn't even the most jaw-dropping part. It's how unbelievably wide this thing is. Olympus Mons isn't a steep, pointy peak like the mountains you picture. It's a shield volcano, which means it's built up from layer after layer of runny lava flowing out and spreading wide over millions of years, creating this enormous, gently sloping dome. And the base of that dome is gigantic. Olympus Mons is so wide that it would cover the entire state of New Mexico, the whole state. You could lay this single mountain down over New Mexico, and it would blanket basically all of it. Let me really put that in your head. If you were standing on Olympus Mons, the mountain would be so wide and its slope so gradual that you wouldn't even be able to tell you were on a mountain. The curve would be too gentle, the scale too enormous. You'd look toward the edges, and the slopes would just disappear over the horizon, because the thing is bigger than your eye can take in. You'd think you were standing on a vast, slightly tilted plain, not the tallest mountain in the solar system. It's so big it stops registering as a mountain at all. So why does Mars get to have a monster like this when Earth, a bigger, more active planet, tops out at Everest? And the answer comes down to a couple of clever differences between the two worlds. First, plate tectonics. Here on Earth, the surface is broken up into giant plates that are slowly moving around all the time. So when you've got a hot spot of magma welling up under the crust, building a volcano, the plate keeps sliding along over it. The volcano drifts off the hot spot, goes quiet, and a new volcano starts forming next to it. That's actually how the Hawaiian Islands formed. A whole chain of volcanoes. Each one carried off the hot spot before it could get too big. Earth's moving crust spreads the volcanic output across many smaller mountains instead of one giant one. Mars doesn't do that. Mars doesn't have moving plates like Earth. Its crust just sits there, one solid, stationary shell. So when a hot spot of magma started pumping lava up to the surface on Mars, the crust above it never moved. The volcano stayed parked right on top of the source for millions and millions of years, just piling lava on top of lava on top of lava in the exact same spot, building higher and higher and wider with nothing to interrupt it. All that volcanic energy got dumped into one single, ever-growing mountain instead of getting spread out. And second, gravity. Mars is smaller than Earth and has weaker gravity, only about a third of what we feel here. And weaker gravity means a mountain can grow taller before its own weight starts to crush it down and slump it over. On Earth, our stronger gravity puts a ceiling on how high a mountain can pile up before it basically can't support itself anymore. Mars's gentler grip lets a mountain reach heights that would be impossible here. So you've got a volcano sitting on a motionless crust, fed for ages, growing in low gravity that lets it keep climbing. Stack all that up over millions of years, and you get Olympus Mons, a monument to deep time and patience. And here's a quieter thought to leave you with on that one. Olympus Mons probably hasn't erupted in a very long time. It's likely dormant now, maybe even extinct. So it stands there, this colossal, silent giant, the biggest mountain in the solar system, towering over a cold, red desert with nobody around to see it. It just sits in the thin Martian wind, holding the record, waiting, quiet, again, always quiet. The biggest things out there make no sound at all. Now let me end this drift with the one that's closest to you. Closer than Mars, closer than Venus, closer than anything. It's the thing you see literally every single day and never think about. Sunlight. Here's the simple version of the fact, and then I'm going to take you on the journey behind it, because the journey is unreal. Every sunrise you see is 8 minutes old. The light hitting your face right now, if you're outside, left the sun about 8 minutes ago. Let me explain why. The sun is about 150 million kilometers away from Earth. That's a huge distance, the biggest distance in your everyday life by far. And light, even though it's the fastest thing in the universe, traveling at about 300,000 kilometers every second, still takes time to cross a gap that big. Specifically, it takes about 8 minutes and 20 seconds for light to travel from the surface of the sun all the way to your eyes, which leads to a genuinely spooky thought. You never actually see the sun as it is right now. You always see it as it was 8 minutes ago. The sun you look at, that bright disk in the sky, that's a picture from the past. If the sun were to suddenly vanish this instant, just blink out of existence, you wouldn't know for another 8 whole minutes. The sky would stay bright, the warmth would keep coming, everything would feel completely normal, and then, 8 minutes later, the last of the light would arrive, and darkness would fall. You're always living 8 minutes behind the sun. Every sunrise is, in a sense, a memory. But okay, that 8 minutes, that's just the easy part. That's just the trip across empty space from the sun's surface to you. Here's where it goes from cool to absolutely mind-bending, because the light didn't start at the sun's surface. It started deep inside, in the core. And the journey it took just to get out of the sun makes that 8-minute trip look like nothing. Let me take you inside the sun, right at the very center, in the core. That's where the magic happens, where the sun makes its energy. Under unimaginable pressure and heat, hydrogen atoms are getting crushed together and fused into helium. And that fusion releases energy in the form of light, little packets of light called photons. So a photon is born, right there in the heart of the sun, carrying the energy that will one day warm your skin. Now you'd think that photon just shoots straight out, right? Travels at light speed, zips out of the sun in a couple of seconds and heads for Earth. Nope. Because the inside of the sun is unbelievably dense, packed so tightly with particles that the photon can't go anywhere in a straight line. It travels a tiny distance, smacks into a particle, gets absorbed, gets spat back out in a random direction, travels another tiny distance, smacks into something else and gets bounced again, over and over and over. It's like trying to walk straight across a stadium that's completely packed shoulder to shoulder with people, except every person grabs you and shoves you in a random direction before letting go. You'd be bouncing around for ages, barely making progress toward the exit. That's what the photon does inside the sun. It zigzags. It ping-pongs through that dense interior in a chaotic, random, drunken stagger, getting absorbed and re-emitted countless times, going forward a little, backward a little, sideways a lot, very slowly, on average, working its way outward toward the surface. Scientists call this a random walk, and it is agonizingly slow. How slow? Here's the part that should genuinely stop you in your tracks. That energy, that light born in the core of the sun, can take hundreds of thousands of years to fight its way out to the surface. Some estimates run into the tens of thousands of years, others much longer, hundreds of thousands, depending on the exact path. Either way, we are talking about an unfathomable amount of time spent just trying to escape the inside of one star. So put the whole journey together now, because this is the payoff. The energy in the sunlight warming your face today was created in the core of the sun an incredibly long time ago. Hundreds of thousands of years ago. Think about what was happening on Earth back then. Our ancient ancestors were just beginning to figure out fire. There were no cities, no writing, no civilization, no recorded history of any kind. Mammoths walked the earth. That long ago, the energy now lighting your morning was already bouncing around inside the sun, beginning its impossibly slow climb toward the surface. And it bounced, and it zigzagged, and it crawled outward across all those thousands of generations of human life, while entire ages of history rose and fell down here, until finally, after that unimaginable journey, it reached the surface of the sun. And then it broke free, and then it crossed 150 million kilometers of empty space in 8 minutes and 20 seconds. And then it landed on you, just now, just like that. So the next time you step outside and feel the warmth of the sun on your skin, I want you to remember what that warmth actually is. It's not fresh, it's not new. It is ancient energy, born before human history, that spent longer escaping a single star than our entire civilization has existed, and then finished the trip in the blink of an eye to touch your face on an ordinary day. The most everyday thing in your life, sunshine, is one of the oldest things you'll ever touch, and that, basically, is the whole secret of this place. The solar system looks calm. It looks peaceful and slow and quiet and serene. A soft blue planet here, a golden ringed one there, a warm yellow sun overhead. But underneath all that calm is some of the most extreme violence and strangeness imaginable. Supersonic storms screaming through frozen darkness on Neptune, diamonds raining down through the crushed insides of ice giants, a backward world where the day outlasts the year, a planet's crown of rings melting away before our eyes, an invisible world summoned out of nothing by pure math, a mountain so vast it would bury an entire state, and sunlight on your skin that's older than human history. None of it makes a sound. That's the thing that gets me every time. All of this, the storms, the diamonds, the dying rings, the giant volcano, the ancient light, every bit of it is happening, or has happened, in total, perfect silence. The universe doesn't announce any of it. It just does it, quietly, endlessly, whether anyone's watching or not. And you get to be here, on this one little rock, for this one little sliver of time, aware of it, able to look up and actually know. That's the part that should never stop feeling incredible. Let me linger on Neptune one more beat, because I don't think you fully appreciated the storms yet. When Voyager went past and clocked those winds, scientists genuinely doubted their own instruments at first. Winds at the equator of Neptune don't just blow. They blow against the planet's own rotation, ripping westward while the planet spins eastward beneath them, a kind of permanent atmospheric rebellion. And the colder a planet is, the calmer it should be. That's the rule everywhere else. Neptune is the coldest major planet, with cloud-top temperatures plunging to around 200 degrees below 0 Celsius, and yet it's the windiest. It's the exact opposite of what should happen, which is precisely why it's so good. The coldest place runs the fastest winds. Make that make sense. We barely can. And here's a little extra on that internal furnace idea. Neptune radiates more than 2 times the energy it receives from the sun, more than double, where Uranus, its near twin in size and composition, is oddly sluggish and seems to leak almost no internal heat. Neptune is pumping warmth up from deep inside, and nobody fully agrees on why 2 planets so similar behave so differently. That mystery heat is probably feeding the storms, driving convection up through the atmosphere and powering those supersonic gales. So the planet is basically self-heating in the dark, generating its own weather from the inside out, billions of kilometers from any sunlight worth mentioning. A world keeping itself awake by its own fire. And circle back to the diamonds for one more thought, because there's a detail I love. Some researchers think these diamonds, once they form, don't just fall and stop. They think the diamonds might sink slowly through the planet's interior over very long timescales, and as they fall through that hot, dense fluid, they release gravitational energy, friction, heat, contributing to the planet's internal warmth, which means the diamond rain itself might be part of what keeps these planets cooking inside. The treasure isn't just a byproduct, it might be part of the engine, falling gems, helping to power a world. You could not write that, and yet there it is, very likely happening, right now, in the cold and the dark, at the edge of everything you know. Think about Venus once more too, because the backward spin has a consequence I didn't give you. On Venus, because it spins backward and so slowly, the relationship between its day and its solar day, the time from one sunrise to the next, gets genuinely strange. Even though it takes 243 Earth days to physically rotate once, the combination of that slow backward spin and its motion around the sun means the time from one sunrise to the next works out to around 117 Earth days. So even the way the sun appears to move across the Venusian sky is its own weird, slow, reversed rhythm. Nothing like the clean 24-hour cycle you take for granted. Imagine waiting almost 4 Earth months between one sunrise and the next, and watching that distant, smothered sun crawl across the sky in the wrong direction the entire time. It's a world running on a completely different clock, in a completely different gear, turning the wrong way. And the rings of Saturn, just to seal that one in your memory. We happen to be alive at the one moment we can see them, and we're also alive at the one moment in human history when we have the tools to understand them. For all of human existence before the telescope, nobody even knew Saturn had rings. Galileo first saw them in 1610 and couldn't even tell what they were. His telescope was too crude, and he thought Saturn had handles, or ears, 2 blobs on either side. It took decades more before anyone realized they were rings at all. So the entire span of humanity actually understanding what those rings are, what they're made of, that they're raining away, is just a few centuries old. A flicker, opening right as the rings themselves are in the slow process of fading. We showed up exactly in time to watch something beautiful while it lasts. That's either a coincidence, or it's the most poetic timing in the universe. So there's your relaxing drift through the solar system. Diamond rain, backward worlds, vanishing rings, summoned planets, a mountain that swallows a state, and light older than civilization landing soft on your face. Quiet violence, all the way down. The calmest looking place you'll ever know, secretly running on chaos. And somehow that makes it more beautiful, not less. Now go look up. There's a whole silent storm up there, and you're one of the only things in the universe that gets to notice. Now, let me keep this drift going, because I left some of the strangest stuff out there in the dark, and you're not done being amazed yet. We covered the planets, the rings, the light, but the solar system is way more than 8 planets and a sun. It's full of moons that are weirder than the planets they orbit, asteroids that hold the recipe for life, comets that are basically dirty time capsules from the dawn of everything, and a whole frozen graveyard of worlds out past Neptune that we're only just beginning to understand. So let's keep falling outward and inward and sideways through more of this beautifully violent place. Let me start with a moon, not our moon, a moon of Jupiter, one that, if it were orbiting the sun on its own instead of a giant planet, we'd absolutely call a planet. Its name is Io, and it is, hands down, the most volcanically active object in the entire solar system. More active than Earth, more active than anything. Here's the picture. Io is roughly the size of our own moon, a little bigger, and you'd expect something that small, that far from the sun, way out at Jupiter, to be a cold, dead, cratered rock, just like our moon is. Frozen, still, lifeless. That's what small moons do. They cool down, they freeze solid. They sit there for billions of years collecting impact craters and doing absolutely nothing. Io did not get the memo either. Io is on fire, constantly. It's got hundreds of active volcanoes scattered across its surface, and some of them are erupting so violently that they blast plumes of sulfur and gas hundreds of kilometers straight up into space. Not into an atmosphere, because Io barely has one. Straight up into the vacuum, fountains of volcanic material shooting up so high they'd dwarf anything Earth has ever produced. The surface is this hellish, churning landscape of orange and yellow and red and black, painted with sulfur and constantly being repaved by fresh lava. There are lava lakes. There are volcanic hotspots glowing so hot you can detect them from across the solar system. Io is a tiny moon that behaves like a planet-sized furnace. So here's the obvious question. How? How is a small moon, far from the sun, this insanely active when our moon, the same kind of size, is stone cold dead? Where is all that heat coming from? Because volcanoes need heat, and small worlds are supposed to lose their heat fast and go quiet forever. Let me explain. Because the answer is one of the most beautiful pieces of physics in the whole solar system. It's called tidal heating, and it comes down to a brutal gravitational tug of war. Io orbits Jupiter, and Jupiter is the biggest, most massive planet there is, with absolutely monstrous gravity. That gravity pulls on Io enormously hard. But Io isn't alone out there. It's got siblings, other big moons of Jupiter, especially Europa and Ganymede, orbiting nearby. And as those moons swing past, their gravity tugs on Io too, pulling it slightly this way and that, nudging its orbit so it isn't a perfect circle. And here's where the violence comes in. Because Io's orbit gets pulled into a slightly stretched, oval shape. The distance between Io and Jupiter keeps changing as it goes around. Sometimes it's a bit closer to Jupiter, sometimes a bit farther. And Jupiter's gravity is so strong that when Io gets closer, the moon literally gets squeezed and stretched. The whole solid body of the moon flexing, the surface rising and falling by as much as 100 meters. The entire moon is being kneaded like a stress ball, flexed and squished over and over, every single orbit, forever. And what happens when you flex something over and over? It heats up. Bend a paperclip back and forth fast enough and the metal gets warm, even hot, right at the bend. That's friction, internal friction, generating heat. Now scale that up to an entire moon being flexed by the gravity of the biggest planet in the solar system, relentlessly, for billions of years. That constant flexing generates an absolutely enormous amount of heat deep inside Io. So much heat that the interior melts, and that molten rock forces its way to the surface as those hundreds of volcanoes. Io isn't warmed by the sun, it's warmed by gravity. It's being squeezed into a fever by Jupiter's grip. And that's the crazy part, when you really sit with it. There's a whole other way for a world to stay hot and alive that has nothing to do with sunlight. Pure gravity, pure tidal stress, can keep a moon molten and erupting billions of kilometers from the sun, out in the cold and the dark, where nothing should be warm. Io is a furnace lit by physics, not by fire, and it never stops, because Jupiter never lets go and the other moons never stop yanking. It's been getting squeezed since the solar system formed, and it'll keep getting squeezed for as long as it exists. A small, dead-looking rock that's actually the most alive, most violent surface anywhere near us. And here's why that matters beyond just being cool. Because once scientists understood tidal heating, they realized something huge. If gravity can keep Io molten, it can keep other moons warm too. Not molten, maybe, but warm enough to do something even more interesting. And that brings me right to Io's neighbor, the moon right next door in line, Europa. Now Europa might be the single most exciting place in the solar system, and I'm not exaggerating, because Europa might have life. Let me build this for you properly. From the outside, Europa looks calm and peaceful, almost boring. It's one of the smoothest objects in the entire solar system. Most moons and planets are covered in craters, scars from billions of years of asteroid impacts. Our moon is absolutely pockmarked with them. But Europa is weirdly smooth, weirdly clean, a bright, pale, icy surface with very few craters at all. And right away, that's a clue, because a surface with no craters is a young surface. It means something is constantly erasing the craters, repaving the surface, wiping the record clean. Something active is going on. What covers Europa is ice. A shell of water ice wrapped all the way around the moon. And crisscrossing that ice are these long, dark cracks and ridges, reddish-brown streaks running across the whole surface, like the lines on a cracked sheet of frozen lake. And here's the thing those cracks are telling us. Underneath that icy shell, scientists are now extremely confident there is an ocean, a real, liquid, saltwater ocean. Not a little pool, a global ocean, wrapped entirely around the moon beneath the ice, and possibly containing more than twice as much water as all of Earth's oceans combined. Let that sink in. A small frozen moon out at Jupiter is holding more liquid water than our entire planet. And how does a moon that far from the sun keep an ocean liquid instead of frozen solid all the way through? Same answer as Io, tidal heating. Europa gets flexed and squeezed by Jupiter's gravity too, just not as extremely as Io. Enough to generate heat deep inside, enough to keep that vast ocean from freezing, enough to keep it sloshing around in liquid form under the protective shell of ice. Gravity again. Gravity keeping water warm where the sun never could. So now line up the ingredients for life as we understand it. You need liquid water. Europa's got an entire ocean of it. You need energy. The tidal heating provides that. And there may be hydrothermal vents on the ocean floor, just like the ones here on Earth's deep seabed, where, by the way, some scientists think life on our own planet may have first gotten started. In the dark, around those hot, mineral-rich vents, with no sunlight at all. And you need the right chemical building blocks, the carbon and other elements life is made from. And there's good reason to think Europa's ocean has those too. Water, energy, chemistry, hidden under the ice. Which means that right now, while you go about your day, there could be a dark, warm, salty ocean on a moon of Jupiter, with hydrothermal vents glowing on its floor. And we genuinely do not know whether something is swimming around in it. Maybe nothing. Maybe just microbes. Maybe something more. We don't know. And that not knowing is the most thrilling thing in space science right now. It's why we're sending a spacecraft, a mission built specifically to study Europa, to fly past it again and again, and sniff out exactly what's going on under that ice. We are actively going to find out. And here's the thought that gets me every time. The ocean on Europa has been there, dark and warm and stable, for billions of years. On Earth, life got started in our ocean in what might have been a similar setting, and it only needed time and the right conditions. Europa has had both, so either life is something special and rare that only happened here, or it's something that happens wherever you've got water, warmth, and time, in which case there might be a second living ocean right next door in our own solar system. Either answer changes everything about about how you see your place in the universe, and we're this close to checking. Now, speaking of water in unexpected places, let me take you somewhere even more surprising than a moon of Jupiter. Let me take you to the moon, our moon, the one you've looked at your whole life and assumed was a bone-dry, dusty, dead ball of gray rock. For a long time, that's exactly what everyone thought. The moon is dry. The Apollo astronauts walked on it, brought back rocks, and the picture was clear. A parched, airless, lifeless desert with not a drop of water anywhere. The most famous dead rock in the sky. And honestly, given how close it is and how harshly the sun beats down on it with no atmosphere to shield it, that made total sense. Any water should have baked off and escaped into space billions of years ago. But here's the twist, and it's a recent one, because our understanding of the moon has flipped in just the last couple of decades. There's water on the moon. Real water, and not just a hint of it, more than we ever imagined. Let me explain where it's hiding. The moon doesn't tilt much on its axis, which means at its north and south poles, there are deep craters whose floors never, ever see sunlight. Ever. The sun is always low on the horizon at the poles, and these crater bottoms are so deep and so positioned that the sunlight literally never reaches the floor. These are called permanently shadowed regions, and they are some of the coldest places in the entire solar system, colder than the surface of Pluto, plunging to hundreds of degrees below zero. And in those frozen, eternal night crater floors, there is water ice, trapped, locked away in the cold and the dark, possibly for billions of years. Think about how that happens. Over the eons, comets and water-rich asteroids have crashed into the moon, and some of that water, instead of baking off, migrated across the surface and got trapped in these freezing, shadowed craters where it could never warm up enough to escape. So it just accumulated, frozen solid, sitting in the dark, untouched, a hidden reservoir of ice on a world everyone wrote off as bone dry. And it's not only in the deep, dark craters. Scientists have also detected water molecules bound up in the sunlit soil across much of the moon's surface, water locked into the lunar dust itself. Even in regions that do get sunlight, it's spread out, it's thin, but it's there, far more widespread than anyone expected. The moon, it turns out, is not the dry desert we thought. It's quietly holding water all over the place. And here's why this is one of the most important facts on this whole list, not just a fun bit of trivia. Water on the moon changes everything about humanity's future in space. Because water isn't just for drinking. You can split water into hydrogen and oxygen to breathe, and hydrogen plus oxygen is rocket fuel. So if there's water on the moon, and we can get to it, then the moon becomes a gas station, a refueling stop. Instead of hauling every drop of water and every ounce of fuel up from Earth at enormous cost, fighting against Earth's gravity the entire way, future explorers could mine water right there on the moon, drink it, breathe from it, and fuel their ships with it for the next leg of the journey, out to Mars and beyond. The moon stops being a dead end and becomes a launch pad. So the dusty gray rock you've ignored your whole life is sitting up there with frozen water hidden in its shadows. And that water might be the key that finally lets humanity push out into the rest of the solar system for good. Turns out the dead rock isn't so dead and isn't so useless after all. It was holding on to something precious the whole time, in the one place we never thought to look, the dark. Now let me jump to something that flies past us all the time, something you've probably wished on without thinking about what it actually is: comets. Because comets are not just pretty streaks of light. Comets are time machines. Here's what a comet actually is. Way out in the cold outer reaches of the solar system, far beyond the planets, there are countless leftover chunks from the very beginning, the rubble that never got swept up into a planet when everything formed 4.5 billion years ago. A lot of these are basically dirty snowballs, big clumps of ice, frozen gases, dust and rock, drifting in the deep cold, far from the sun's warmth. warmth. And out there, in the freezer, they've stayed almost perfectly unchanged since the solar system was born. They're pristine. They're frozen samples of the original ingredients that everything, the planets, the sun, you, was made from. Now every so often one of these icy bodies gets nudged, maybe by the gravity of a passing star or the pull of a distant planet, and it falls inward, plunging toward the sun on a long looping orbit. And as it gets closer to the sun and starts to warm up, the magic happens. The frozen ices on its surface don't melt into liquid. They sublimate, turning straight from solid into gas. And that gas, along with the dust trapped in it, streams off the comet, forming that glowing head and that long, beautiful tail streaking across the sky. That tail, by the way, always points away from the sun, blown back by the solar wind and the sun's light. So even when a comet is heading away, its tail streams out ahead of it. The thing you see and wish on is a 4.5 billion-year-old snowball melting in the sunlight. And here's why that's so precious, why scientists get so excited about comets. Because they're so old and so unchanged. Comets are like frozen postcards from the birth of the solar system. Studying them is like opening a time capsule and looking at the raw materials that everything else was built from. And we've actually done it. We landed a spacecraft on a comet. In 2014, the Rosetta mission, after a journey of 10 years across the solar system, dropped a small lander called Philae down onto the surface of a comet. The first time in history we ever soft landed on one of these things. We chased down a dirty snowball hurtling through space and gently set a robot on top of it, just to read the time capsule up close. And what we found in comets is genuinely staggering. Comets contain water. They contain organic molecules, the carbon-based building blocks that life is made from. And this leads to one of the biggest, most profound ideas in science. Where did Earth's water come from? Where did the ingredients for life come from? When Earth first formed, it was a hot, hellish, molten ball, way too hot to hold onto water. So how did our planet end up with vast oceans and all the chemistry needed for life? One of the leading theories is that comets and water-rich asteroids delivered it. That during the early, chaotic days of the solar system, when impacts were constant, countless comets and asteroids slammed into the young Earth, and they brought water, and they brought those organic molecules, raining the ingredients for oceans, and possibly for life itself down onto our planet from space. Which means the water in your body, the water you drank this morning, may have ridden in on a comet billions of years ago. And the carbon building blocks that make up you may have been delivered by the same kind of dirty snowballs you've watched streak across the night sky. Sit with that for a second. You might be made, in part, of comet. The oceans might be ancient comet water. Life itself might have gotten its starter ingredients hand-delivered from the deep frozen edge of the solar system. So the next time a comet swings by, you're not just looking at a pretty light. You might be looking at the same kind of object that brought the raw materials for everything you are. A time machine, a delivery truck, and a wishing star, all in one frozen ball of ice and dust. Now, while we're talking about leftover rubble from the birth of the solar system, let me clear up something you've definitely got wrong in your head, because Hollywood has lied to you about it for decades. The asteroid belt. When you hear asteroid belt, what do you picture? Be honest. You picture that classic movie scene, right? The hero's spaceship weaving and dodging frantically through a dense, churning cloud of giant tumbling rocks. Rocks slamming into each other everywhere, the pilot barely threading the needle, near misses on every side, the whole screen packed with deadly boulders. That's the asteroid belt in your imagination, a chaotic, crowded demolition derby of rock. Yeah, that's completely wrong. Almost the exact opposite of the truth, actually. Let me explain. The asteroid belt is real. It's a region between the orbits of Mars and Jupiter, a big donut-shaped zone full of asteroids, leftover rocks that never managed to clump together into a planet, partly because Jupiter's enormous gravity kept stirring them up and preventing it. And there are a lot of asteroids in there, millions and millions of them, ranging from tiny pebbles to one object, Ceres, that's big enough to be classified as a dwarf planet, nearly 1,000 kilometers across. So with millions of asteroids, it must be crowded, right? Wrong. Because here's the thing people never grasp. Space is unimaginably, mind-bendingly huge, and the asteroid belt is enormous. That donut-shaped region is so vast that even with millions of asteroids spread through it, they are spectacularly far apart. On average, the distance between one asteroid and the next is something like hundreds of thousands, even millions of kilometers. We're talking distances comparable to the gap between the Earth and the Moon, or more, between one space rock and the next. Let that reset your imagination. If you were standing on an asteroid in the belt, you would almost certainly not be able to see another asteroid with your naked eye. You'd look around and see nothing but empty black space in every direction, the same as anywhere else. You wouldn't be dodging anything. There'd be nothing to dodge. The belt is, for the most part, profoundly, overwhelmingly empty. And here's the proof. We have flown spacecraft straight through the asteroid belt, many of them. Every probe we've sent to the outer solar system, to Jupiter, Saturn, and beyond, has had to pass right through the belt to get there, and not a single one has ever had to dodge anything, not once. In fact, the belt is so empty that when scientists want to fly a spacecraft past a specific asteroid to study it up close, they have to aim very carefully and burn fuel to deliberately steer toward one, because the odds of just randomly bumping into an asteroid are basically zero. The danger isn't hitting too many of them. The challenge is finding one at all. So the dramatic, crowded, dodge-em-up asteroid field of the movies is pure fiction. The real asteroid belt is a vast, lonely, near-empty expanse where millions of rocks drift through such enormous distances of nothingness that they almost never come anywhere near each other. It's one of the emptiest places you can imagine, hiding behind one of the most action-packed reputations. Turns out the scariest sounding place in the solar system is actually one of the loneliest. And I bring that up not just to correct the movies, but because it teaches you the single most important and hardest thing to truly feel about space. The defining feature of the solar system isn't the planets, or the moons, or the rocks. It's the emptiness, the distances, the sheer, staggering amount of nothing between everything. We draw the planets all bunched up close together in textbook diagrams, but that's a complete lie, a necessary lie to fit them on a page. In reality, they're scattered across distances so vast that your brain literally cannot picture them properly. And the asteroid belt, that supposedly crowded danger zone, is the perfect proof of just how empty this place really is. Now let me push you even farther out, past Neptune, past everything we've talked about, to the cold, dim, frozen frontier at the edge of the solar system, a place called the Kuiper Belt. And the most famous resident of that frozen frontier, the one you definitely have feelings about, Pluto. Okay, Pluto. Poor Pluto. You grew up, maybe, learning it was the 9th planet, the little guy at the end of the line. And then, in 2006, scientists got together and demoted it, reclassified it as a dwarf planet, and a whole lot of people were genuinely upset about it, like a beloved member of the family had been kicked out. So let me actually explain what happened, because it's more interesting than people think, and it's not the insult it sounds like. Here's the deal. When Pluto was discovered in 1930, it seemed like a lonely little world way out past Neptune, the last planet, the edge of the map. For decades, that's how it was taught. But then, as our telescopes got better, especially toward the end of the 20th century, astronomers started finding more stuff out there. A lot more stuff. They discovered that Pluto wasn't alone at all. It was sitting in the middle of a whole vast region of icy bodies. That frozen frontier I mentioned, the Kuiper Belt, packed with countless frozen worlds and chunks of ice circling the sun out in the deep cold beyond Neptune. And then came the moment that sealed Pluto's fate. Astronomers found another object out there, named Eris, that was roughly the same size as Pluto, and at first it even looked bigger and more massive. And that created a problem, because if Pluto is a planet, then Eris has to be a planet too. And if Eris is a planet, then what about all the other big, round, icy objects we kept finding out there? Suddenly the solar system wasn't looking at 9 planets. It was looking at potentially dozens, maybe more, as we kept discovering Pluto-sized things in the Kuiper Belt. Either you let the list of planets balloon into the dozens, or you tighten up what the word planet actually means. So scientists chose to define it properly, and they came up with a few rules for what makes a planet. It has to orbit the sun. Check. Pluto does that. It has to be big enough that its own gravity has pulled it into a round shape. Check. Pluto's round. And the third rule, the one Pluto fails, is that it has to have cleared its neighborhood, meaning it has to be gravitationally dominant in its orbit, big enough to have swept up or flung away all the other debris around its path. The 8 planets have done this. They're the bosses of their orbits. But Pluto hasn't. Pluto orbits right in the middle of the Kuiper Belt, surrounded by tons of other icy bodies, sharing its space, not dominating it. It's one resident of a crowded, frozen neighborhood, not the king of an empty one. So Pluto got reclassified as a dwarf planet. And honestly, that's not a demotion so much as a more accurate description. It didn't shrink. It didn't disappear. We just understood it better. Pluto became the most famous member of a whole new category of world, and the king of the Kuiper Belt, rather than a runt at the back of the planet line. And here's the part that should make you stop feeling sad for Pluto, because Pluto turned out to be way cooler than anyone expected. For almost its entire history of being known to us, Pluto was just a tiny, blurry dot, even in our best telescopes. A fuzzy speck. Nobody had any idea what it actually looked like. Then, in 2015, a spacecraft called New Horizons, after a journey of 9.5 years and 3 billion miles, finally flew past Pluto and sent back the first close-up pictures in human history. And Pluto blew everyone away. People expected a dead, boring, cratered ball of ice, basically a slightly more interesting asteroid. Instead, New Horizons revealed an astonishingly complex and active world. Pluto has towering mountains made of water ice, mountains as tall as the Rockies, because out there it's so cold that water ice is hard as rock. It has vast, smooth plains of frozen nitrogen. And here's the wild part. Those plains show signs of churning and flowing, glaciers of frozen nitrogen slowly moving and resurfacing the landscape, which means Pluto is geologically active, still alive in a sense, billions of years after forming, way out in the deep freeze where it has no business being active at all. And the most famous feature, the one that made everyone fall in love, is a giant, bright, heart-shaped region on its surface, a vast plain of ices that, from a distance, looks exactly like a heart. Pluto, the world we kicked out of the Planet Club, sent back its first ever portrait with a giant heart on its face. You can't write that. The universe has a sense of humor. So Pluto isn't a sad story. Pluto is a triumph. It taught us that the solar system is bigger and richer than we thought, full of whole categories of worlds we didn't even know existed. And when we finally went out to meet it, it turned out to be one of the most surprising, beautiful, and active little worlds in the entire system. Not a failed planet, a spectacular dwarf one, ruling a frozen frontier we're still mapping today. And that frozen frontier, the Kuiper Belt, is genuinely the edge of the explored solar system. But it's not the actual edge. Way, way beyond it, scientists believe there's an even more distant, even colder region called the Oort cloud, a vast spherical shell of icy bodies surrounding the entire solar system at unimaginable distances. So far out it might extend a good fraction of the way to the nearest other star. We've never seen it directly. It's too far and too faint. But we think it's the source of those long-period comets, the dirty snowballs that occasionally fall in from the deep dark to streak across our sky. The Oort cloud is so distant that the spacecraft we launched in the 1970s, the Voyagers, which have already left the planets behind and crossed into interstellar space, won't reach the Oort cloud for another 300 years, and won't pass through the far side of it for tens of thousands more. That's how big this thing is. Our fastest, farthest flung machines need tens of thousands of years just to cross the outermost shell of our own solar system. The place you live in is so vast that we've barely fingertipped the edge of it. And let me circle that back to the theme, because it all connects. Everything we've talked about, the volcanoes squeezed alive by gravity, the hidden ocean that might hold life, the water lurking in the moon's shadows, the comets carrying the ingredients of life across billions of years, the deceptively empty belt, the demoted dwarf with a heart on its face, the unimaginable cloud at the edge, all of it tells you the same thing. This place is bigger, stranger, older, and more alive than it has any right to be, and almost none of it looks the way you'd guess from down here. Think about Io one more time, because there's a detail that makes it even more extreme. The volcanic plumes on Io are so powerful and so high that the material they blast out doesn't all fall back down. Some of it escapes Io entirely and gets flung out into space, where it gets caught up by Jupiter's gravity and its enormous magnetic field. This creates a giant donut-shaped cloud of charged particles around Jupiter, fed directly by Io's eruptions, a torus of glowing plasma circling the giant planet, made of stuff vomited up by a tortured little moon. Io is literally feeding its own material into the space around Jupiter, painting an invisible ring of plasma around its tormentor. The squeezing never stops, the eruptions never stop, and the moon keeps bleeding its insides out into Jupiter's grip. It's the most dramatic relationship in the solar system, a moon and a planet locked in a billion-year gravitational vice. And think about Europa's ocean one more time, because there's a thought that genuinely keeps scientists up at night. If there is life in Europa's ocean, it would be the first life we've ever found anywhere besides Earth. And here's the kicker. It would have arisen completely independently from us. There's no way for life from Earth to have gotten to Europa's subsurface ocean, and vice versa. They're sealed off, separate, hundreds of millions of kilometers apart, and locked under kilometers of ice. So if we find even a single microbe in that ocean, it means life started twice, independently, in just one solar system. And if life can start twice in one ordinary solar system, then the universe, with its hundreds of billions of solar systems in our galaxy alone, must be absolutely teeming with it. One microbe under that ice would rewrite the answer to the biggest question humans have ever asked. Are we alone? That's why we're going. That's what's at stake under that quiet, smooth, frozen surface. And think about the comets and the moon's water together, because they're really the same story. Both are about water and the ingredients of life turning up where you'd never expect them, in the cold, in the dark, in the shadows, in the frozen rubble. The picture that emerges from all of it is that water, the one thing life absolutely needs, is not rare and special and confined to Earth. It's everywhere. It's in the moon's frozen craters. It's in the comets falling in from the edge. It's in a global ocean under Europa's ice. It's likely in the soil of Mars and locked into asteroids all over the place. The solar system is wet in all the places we assumed were dry. And where there's water and warmth and time, well, you already know what might follow. So here's where this leg of the drift leaves you. You started this thinking of the solar system as the sun and a handful of planets, a tidy little diagram. But it's so much more than that. It's a furnace moon squeezed alive by gravity. It's a hidden ocean that might be home to something swimming in the dark. It's a dead-looking rock, secretly hoarding water that could carry us to other worlds. It's frozen time capsules delivering the building blocks of life across billions of years. It's a belt so empty it shatters every movie you've seen. It's a demoted little world that turned out to have a heart and a beating geological pulse. And it's a cloud of ice so vast and distant, our fastest machines need tens of thousands of years to cross it. All of it quiet, all of it patient, all of it happening right now, whether you look up or not. And you, sitting wherever you are one tiny conscious speck on one small wet rock, somehow able to know all of this. To send robots to land on comets and fly past Pluto and hunt for oceans under alien ice. That's the part that should never get old. The solar system has been running its quiet, violent, beautiful machinery for 4.5 billion years in near total silence. And only now, in this one flickering moment, is there finally something here capable of noticing. That something is you. So keep noticing. We're nowhere near done. Now, let me drag you back inward, all the way to the center of everything, because we've spent a lot of time out in the cold, dark edges, and we've barely talked about the thing that runs the whole show, the sun. You've looked at it 1,000 times, you've felt it on your skin, and you have absolutely no idea how insane it actually is. So let me fix that, because the sun is the most extreme object you will ever personally see with your own eyes. Here's the first thing that should mess with you. The sun is so big that it makes up about 99.8% of all the mass in the entire solar system. Let that number sink in. Everything else, all 8 planets, all the moons, all the asteroids, all the comets, Jupiter, Saturn, the whole lot of it combined. That's the other 0.2%, the leftovers, the crumbs. When the solar system formed out of a collapsing cloud of gas and dust, almost all of the material fell into the center and became the sun. And what was left over, the tiny scraps that didn't get swallowed, became literally everything else, including you. You are made of the crumbs that the sun didn't eat. The whole rest of the solar system is basically a rounding error compared to the star at the middle of it. And how big is that, really? Let me give you something your brain can actually hold. The sun is so wide that you could line up about 109 Earths across its face, side by side, just to span its diameter. And to fill up its volume, you'd need around 1.3 million Earths. 1.3 million. If the sun were a hollow ball, you could pour over 1 million Earths inside it and still have room to rattle them around. It's not just the biggest thing in the solar system. It's so much bigger than everything else that there's really no comparison. It is the solar system, and everything else is just stuff that orbits it. Now here's where it gets genuinely violent. The kind of violence that makes Neptune's storms look like a light breeze. Let me take you to the core of the sun, the same place where the sunlight you feel was born. But this time, I want you to understand the conditions down there, because they are beyond anything that exists anywhere else near you. At the core of the sun, the temperature is around 15 million degrees Celsius. 15 million. And the pressure is so colossal, the weight of all that overlying material crushing down, that it's something like 250 billion times the air pressure you feel at sea level on Earth. It is the single most extreme environment in the entire solar system, hidden right in the heart of the thing that gives you life. And in that crushing, scalding inferno, the sun does something that, for most of human history, nobody could even imagine. It performs nuclear fusion. Let me explain what that actually means, because this is the engine of everything. Down in that core, the pressure and heat are so extreme that hydrogen atoms, the simplest, lightest atoms there are, get smashed together so hard that they fuse, merging into helium, a slightly heavier atom. And here's the magic. When 4 hydrogen atoms fuse into one helium atom, the helium that comes out weighs just a tiny bit less than the 4 hydrogens that went in. A tiny fraction of mass goes missing. And that missing mass doesn't just vanish. It gets converted directly into pure energy, following Einstein's famous equation, the one that says mass and energy are the same thing, and you can turn one into the other. That tiny bit of lost mass becomes an enormous burst of energy because the equation multiplies it by the speed of light squared, which is a staggeringly huge number. So the sun is taking matter and converting it straight into energy, and it's doing it on a scale that's almost impossible to comprehend. Every single second, the sun fuses around 600 million tons of hydrogen every second, and in doing so, it converts roughly 4 million tons of matter directly into pure energy every second of every day, and has been doing so for 4.5 billion years. 4 million tons of the sun's own substance, vanishing into light and heat every tick of the clock. The sun is quite literally burning away its own body to keep shining, throwing 4 million tons of itself into the void as energy with every passing second. And that energy, that is what crosses 93 million miles of empty space to land on your face, to grow the food you eat, to drive the weather, to power nearly every living thing on Earth. The sun is a colossal, continuous, controlled nuclear explosion, a hydrogen bomb the size of 1 million Earths that has been detonating non-stop for billions of years. And it's held together and balanced so perfectly by its own immense gravity that instead of blowing itself apart, it just shines, steadily, reliably, day after day. That balance, by the way, is one of the most beautiful things in physics. The fusion in the core wants to blast the sun apart, pushing outward with unimaginable force, and the sun's own gravity wants to crush it inward, collapsing it down to a point. And those two titanic forces, the outward push of fusion and the inward crush of gravity, are locked in a perfect standoff, balanced so exactly that the sun holds its shape and size, steady as a rock, for billions of years. It is a permanent explosion that gravity has caged. Quiet violence, the biggest example of it you'll ever know, sitting right there in your sky every single day. And here's a thought to leave you with on the sun. It's not going to last forever. Right now, the sun is middle-aged, about 4.5 billion years old, and it's got maybe another 5 billion years of hydrogen burning left. But eventually, it's going to run low on hydrogen fuel in its core, and when that happens, everything changes. The balance breaks. The sun will swell up into a red giant, expanding enormously, so huge it'll swallow Mercury, then Venus, and possibly reach all the way out to scorch or engulf the Earth itself. The thing that gives us life will, in its old age, very likely destroy the very planet it's been nurturing. And then it'll shed its outer layers into a beautiful, glowing shell of gas, and collapse the core down into a small, dense, slowly cooling ember called a white dwarf, where it will sit, fading, for trillions of years. So the sun has a life and a death, just like everything else. We just happen to be living in its long, calm, perfect middle, the exact stretch where it shines steadily enough for life to exist. Lucky timing. Again, always lucky timing. Now, speaking of the sun being violent, let me tell you about the way that violence reaches all the way out and touches Earth, and gives you one of the most beautiful sights you can ever witness, the Northern Lights, the aurora. Because that gorgeous, gentle, dancing curtain of color in the polar sky is actually the visible result of the sun attacking our planet. I'm not kidding. Let me explain. The sun doesn't just give off light and heat. It also constantly blows out a stream of charged particles, electrons and protons, flowing off its surface in every direction at high speed. This is called the solar wind, and it's washing over the entire solar system all the time, including over Earth. And during especially violent events on the sun, like solar flares and coronal mass ejections, which are enormous eruptions that blast huge clouds of these charged particles out into space, the solar wind can become a solar storm, a powerful surge of particles screaming toward us at millions of kilometers an hour. Now, if those charged particles just slammed straight into Earth, into the atmosphere, into us, it would be catastrophic for life. That radiation would be deadly over time, stripping away our atmosphere and frying living things. But here's the thing that saves us: the invisible shield that makes Earth livable. Earth has a magnetic field. Deep inside our planet, there's a core of molten, churning iron, and that swirling liquid metal generates an enormous magnetic field that wraps all the way around the Earth, extending far out into space. It's invisible, it's silent, and it is constantly protecting you. This magnetic field acts like a force field, deflecting the vast majority of those incoming charged particles, steering them around the planet, keeping the deadly solar wind from reaching the surface. You are alive, in part, because of an invisible magnetic bubble generated by a sea of molten iron thousands of kilometers beneath your feet. But here's where the beauty comes in. The magnetic field isn't a perfect uniform shell. It's shaped a bit like the field around a bar magnet, with the lines of force diving down into the planet at the north and south magnetic poles. So near the poles, some of those charged particles from the sun get funneled down along the magnetic field lines and are allowed to plunge into the upper atmosphere. And when those high-speed particles from the sun crash into the gas molecules in our upper atmosphere, oxygen and nitrogen, they smack into them and pump energy into them, exciting them. And when those energized molecules calm back down, they release that extra energy as light, just like a neon sign, where electricity excites a gas and makes it glow. The solar particles excite our atmosphere and make it glow. That glow is the aurora, the northern lights, and their southern twin, the southern lights. Those shimmering, rippling curtains of green and red and purple dancing across the polar sky are literally the sun's particles colliding with our air, lit up where our magnetic field channels them down. The green you most often see comes from oxygen, the reds and purples from oxygen and nitrogen at different heights and energies. So when you look up at the aurora, you are not just seeing a pretty light, you are watching, in real time, the sun's violence being caught, deflected, and channeled by Earth's invisible shield, and converted into one of the most beautiful sights in nature. It's the visible proof of an invisible battle that's protecting your life. The most peaceful, dreamy thing in the night sky is the glowing evidence of our planet getting hit and surviving over and over. And here's the slightly scary flip side, because remember the theme, quiet violence. A really powerful solar storm doesn't just make pretty lights, it can cause real damage. Big solar storms can knock out satellites, disrupt radio communications, mess with GPS, and in extreme cases, induce surges in power grids that can cause blackouts. Back in 1859, there was a massive solar storm now called the Carrington Event, the most powerful one in recorded history. It was so strong that the aurora was seen as far south as the Caribbean, places that never see the northern lights. And it was so powerful that it overloaded the telegraph systems of the time, the cutting-edge technology of that era, sparking fires and shocking operators, with some telegraph lines reportedly working even after being disconnected, running purely on the electricity the storm pumped into them. Now imagine a storm that size hitting today, with our entire civilization wired together and utterly dependent on satellites, electronics, and power grids. It could be genuinely devastating, knocking out infrastructure across whole continents. So that beautiful aurora is a gentle reminder that the sun is a wild, unpredictable beast, and we live close enough to feel its temper. We just usually only see the pretty side of it. Now let me jump to something completely different, something about how the planets move, because there's a pattern out there that's so strange and so mathematically eerie that it spooked astronomers for centuries, and it ties into a kind of cosmic gravitational dance. Let me talk about how the planets keep their distances and the weird, almost musical order in the way everything orbits. Here's something most people never think about. The planets don't just orbit the sun at random distances, willy-nilly. There's a structure to it, a spacing, and the orbits are remarkably stable, holding steady for billions of years. And the reason they stay stable, the reason the solar system doesn't just descend into chaos with planets crashing into each other or getting flung out into space, comes down to a delicate gravitational balancing act, and one phenomenon in particular called orbital resonance. Let me explain orbital resonance because it's beautiful. Resonance happens when two orbiting bodies have orbital periods, the time they take to go around, that line up in a simple ratio. Like one body going around exactly twice in the same time another goes around once, a 2-to-1 ratio. When that happens, the two bodies keep meeting up in the same relative positions over and over, and their gravitational tugs on each other add up in a regular, repeating way instead of canceling out randomly. And depending on the situation, that can either lock the orbits into a beautifully stable, self-correcting pattern, or it can do the opposite and slowly destabilize things, kicking objects out. Remember those moons of Jupiter we talked about, Io and Europa and Ganymede, the ones whose gravitational tugging keeps Io molten? Those three moons are locked in a perfect resonance, a 1-2-4 pattern. For every one orbit Ganymede makes, Europa makes exactly 2, and Io makes exactly 4. Tick, 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 perfectly in time, like three gears meshing, like three musicians keeping a rhythm together across billions of years. That precise lockstep is exactly what keeps tugging Io's orbit out of round and feeding the tidal heating that powers its volcanoes. So the resonance, that mathematical music in the orbits, is directly responsible for the most volcanic surface in the solar system. The numbers aren't just abstract, they light fires, and resonance shows up all over the place. Remember that supposedly crowded asteroid belt? Within it there are gaps, regions where you find almost no asteroids at all, called the Kirkwood gaps. And those gaps exist precisely where an asteroid's orbital period would line up in a simple resonance with Jupiter's. At those specific distances, Jupiter's gravity gives the asteroid a regular repeated tug every time they line up, and over millions of years those tugs add up and gradually destabilize the orbit, eventually flinging the asteroid out of that zone entirely. So Jupiter, just by existing and orbiting, has carved invisible empty lanes into the asteroid belt, using nothing but the rhythm of resonance. The structure of the belt is sculpted by mathematics, by the timing of orbits, by Jupiter's gravitational drumbeat, clearing out anything that falls into step with it. And this gets at something profound about the solar system, something that took humanity a very long time to understand. The whole thing is a gravitational system in delicate balance. Every object pulls on every other object. The sun dominates, of course, with that 99.8% of the mass, but the planets pull on each other too, nudging and tugging in a complex, endless dance. And over the 4.5 billion years the solar system has existed, that dance has mostly settled into stable, self-sustaining patterns. The planets finding orbits and resonances where they can coexist without destroying each other. But it wasn't always so calm. In the early days, the solar system was a violent, chaotic place, with way more objects, far more collisions, and planets that may have actually migrated, moving inward and outward over time as they gravitationally jostled with each other and flung smaller bodies around. In fact, one leading theory suggests the giant planets, Jupiter, Saturn, Uranus, and Neptune, didn't form exactly where they are now. They may have shifted positions over hundreds of millions of years, with Jupiter possibly migrating inward and then back out, and the ice giants moving around significantly in a great gravitational reshuffling that scattered comets and asteroids all over the solar system, possibly triggering a period of intense bombardment that pummeled the inner planets, including the young Earth and Moon. So the calm, orderly, resonant solar system you see today is actually the survivor, the settled aftermath of an early era of gravitational chaos and migration. The stability is hard-won. It's the peace that came after the war. Now, let me bring this back to something you can actually feel and connect to, because all this talk of gravity and orbits and resonance can start to feel abstract. So let me ground it in the most relatable orbital relationship there is, the one between the Earth and the Moon. Because that relationship is doing something to you right now that you experience all the time and probably never connect to space at all. The tides. Here's the deal. The Moon, even though it's far away, has gravity, and that gravity pulls on the Earth. And crucially, it pulls a tiny bit harder on the side of the Earth that's facing the Moon, because that side is closer, and gravity gets stronger with closeness. So the Moon's gravity tugs on the Earth's oceans, pulling the water on the near side slightly toward the Moon, creating a bulge of water. And, in a slightly less intuitive way, there's a second bulge on the far side of the Earth too, because the solid Earth itself gets pulled toward the Moon a bit more than the water on the far side does, leaving that far water bulging out behind. So you get two bulges of ocean, one facing the Moon and one on the opposite side. And as the Earth rotates underneath those bulges, spinning once every day, the coastlines pass through the bulges, and that's the tide rising. Then they pass through the low spots in between, and that's the tide falling. That's why most coastlines get roughly 2 high tides and 2 low tides every day, as the spinning Earth carries them in and out of those bulges of water that the Moon's gravity is holding up. So every time you've ever stood on a beach and watched the tide come in, you were watching the Moon's gravity reach across hundreds of thousands of kilometers of empty space and pull the entire ocean. You were watching gravity, the same force that keeps the planets in their orbits and squeezes Io into a fever, lift the sea right in front of you. The tides are gravity made visible, the most direct, everyday proof you have that another world is reaching out and touching ours. And the sun plays a part too. The sun's gravity also pulls on the oceans, though because it's so much farther away, its tidal effect is a bit weaker than the moon's, despite the sun being vastly more massive. When the sun and moon line up, at the new moon and the full moon, their gravitational pulls combine, and you get especially big tides, called spring tides, with extra high highs and extra low lows. And when they're at right angles, at the quarter moons, their pulls partly cancel out, and you get gentler tides, called neap tides. So the rhythm of the tides at your local beach is a direct readout of the positions of the sun and moon, a tidal clock written by gravity in the rising and falling of the sea. The cosmos isn't far away and abstract. It's lapping at your feet every single day. And here's a wild bonus to that, something that connects the tides to deep time. The friction of all that tidal sloshing, all those bulges being dragged around the spinning Earth, is very slowly acting as a brake on Earth's rotation. The tides are gradually, imperceptibly slowing the Earth's spin down, which means days are getting longer over time, by tiny fractions of a second per century. Back when the dinosaurs were around, a day was noticeably shorter, only about 23 hours, and go back much further, to the early Earth billions of years ago, and a day may have been only a handful of hours long, with the Earth whipping around far faster than it does now. The moon has been slowly putting the brakes on us for billions of years, lengthening our days, stretching out time itself, through nothing but the patient drag of the tides, and at the same time, by a beautiful law of physics, as the Earth's spin slows down, the moon is slowly drifting away from us, spiraling outward by a few centimeters every year, about the rate your fingernails grow. So the moon is getting farther away, very slowly, all the time. Which means that long, long ago, the moon was much closer, and it loomed far larger in the prehistoric sky. And far, far in the future, it'll be smaller and more distant. And here's a poignant little fact that falls out of all this. Right now, by an astonishing coincidence, the moon and the sun appear almost exactly the same size in our sky, which is the only reason we get those perfect total solar eclipses, where the moon precisely covers the sun's disk and reveals its ghostly outer atmosphere. But because the moon is drifting away, that won't always be true. In the far future, the moon will appear too small to fully cover the sun, and total solar eclipses will become impossible. So we are living once again in a special window of cosmic time, the one era when the geometry just happens to line up perfectly for the most spectacular sky show there is. A little earlier or a little later in cosmic history, and the eclipse, as we know it, simply wouldn't happen. You're starting to notice that, aren't you? How many times the answer comes back to lucky timing. The sun in its calm middle age. Saturn's rings here just for now. The moon at exactly the right distance for eclipses. The rings raining away, the moon drifting off, the sun slowly aging. We keep arriving at this same quiet truth. So much of what makes the solar system beautiful and livable and spectacular is temporary, a phase, a window. And we, somehow, exist right in the middle of all those windows at once, with the awareness to see them and the tools to understand them. That's not just lucky, that's almost unreasonably lucky. And it should make every glance at the sky feel a little more urgent, a little more precious. Now let me give you one more piece of the sun's reach, one more way that distant nuclear furnace shapes your existence, because we've talked about the light and the heat and the solar wind and the aurora, but there's something even more fundamental. The sun and the stars before it literally made you, the atoms in your body. Let me explain, because this might be the single most beautiful fact in all of astronomy, and it ties the whole solar system back to you in the most intimate way possible. Think about what you're made of. Your body is built from atoms, carbon, oxygen, nitrogen, calcium in your bones, iron in your blood, and a bunch of other elements. Now here's the question nobody asks. Where did those atoms come from? They had to come from somewhere. They didn't just appear. And the answer is genuinely staggering. They were forged inside stars. When the universe first began, it was almost entirely just the two simplest elements, hydrogen and a bit of helium. That's it. No No carbon, no oxygen, no iron, none of the heavier stuff that life and rock and planets are made from. So where did all the rest come from? It came from stars doing exactly what the sun is doing right now. Fusion, but taken much, much further. Inside stars, fusion smashes hydrogen into helium, and in bigger, hotter stars, it goes further, fusing helium into carbon, carbon into oxygen, and on up the ladder, building heavier and heavier elements in their cores over their lifetimes. Stars are element factories, cooking up the building blocks of everything out of simple hydrogen. And then, when a massive star reaches the end of its life and runs out of fuel, it dies in a colossal explosion called a supernova, one of the most violent events in the entire universe, briefly outshining an entire galaxy. And that explosion does two things. It forges the very heaviest elements, things like gold and silver, in the unimaginable energy of the blast. And it blasts all of those elements, all the carbon and oxygen and iron and gold the star ever made, out into space, scattering them across the galaxy in a vast, expanding cloud. And those clouds, enriched with all the elements cooked up and flung out by generations of dead stars, are exactly the raw material that new stars and planets form from. Our own sun and solar system, including the Earth, including you, formed about 4.5 billion years ago out of one such cloud, a cloud that had been seeded with the ashes of earlier stars that lived and died before our sun was ever born. So the carbon in your cells, the oxygen you're breathing, the calcium in your bones, the iron in your blood, every single one of those atoms was forged in the heart of a star that died long before the sun existed, scattered across space in a supernova, and eventually gathered up to make this world and everything on it, including you. You are, quite literally, made of stardust, made of the ashes of dead stars. The atoms that make up your body have been around for billions of years, were once inside a blazing star, were flung across the galaxy in an explosion brighter than 1 billion suns, and finally, after an unimaginable journey, came together to become you, a creature that can look up at the stars and wonder where it came from. The universe made beings out of its own ancient star ash, beings capable of looking back up and understanding the very process that created them. That's not poetry, that's physics. You are the universe, made of recycled stars, looking at itself. And every atom in you will go on, long after you're gone, to become part of something else. Soil, plants, other living things. Maybe one day part of another world entirely. You're not separate from the cosmos. You never were. You're made of it. You're a part of its story. And for one brief flicker, you get to be the part that's awake and paying attention. So let's pull all of this together for a second, because we've covered enormous ground. We talked about the sun, that permanent, gravity-caged nuclear explosion holding 99.8% of everything, burning 4 million tons of itself into light every second. We talked about the aurora, the visible proof of the sun's violence being deflected by Earth's invisible magnetic shield. We talked about resonance, the mathematical music that keeps the orbit stable and the gaps carved and Io's volcanoes burning. We talked about the tides, gravity reaching across space to lift the sea at your feet, slowing our days and pushing the moon away. And we talked about the deepest truth of all, that the atoms in your body were cooked in dead stars, and you are, in the most literal sense, stardust contemplating itself. And through every single one of those, the same theme keeps surfacing: quiet violence, lucky timing. A universe that looks calm and serene from your back garden, but is actually running on unimaginable forces, extreme conditions, ancient catastrophes, and delicate balances that took billions of years to settle. The peace you feel looking up at the night sky is real, but it's a peace built on top of staggering chaos, the way a calm lake sits on top of unimaginable depth, and you, a small, warm creature made of star ash on a wet rock with an iron heart and a borrowed atmosphere, get to sit there and take it all in. Think about the sun one more time before we move on, because there's a detail that ties it all together. That fusion in the core, the thing that powers everything, the light, the warmth, the weather, the aurora, the tides indirectly through all the energy that drives our world. It's the same fundamental process that, in bigger stars, forged the atoms you're made of. So the sun isn't just keeping you alive day to day. It's running the exact same kind of engine that built you in the first place. When you feel sunlight on your skin, you're feeling the output of the same process that created the carbon in your hand that's catching the light. The maker and the sustainer are the same kind of fire. There's a unity to it, a circle, the star fire that made you and the star fire that warms you, separated by billions of years, but fundamentally one and the same. And that circle keeps turning. Our sun, in 5 billion years, will die too. Not in a grand supernova, it's not big enough for that, but it'll shed its outer layers into a glowing cloud and seed the galaxy with some of the elements it made, atoms that might one day become part of new stars, new planets, maybe new life. So even the sun, the giver of everything we have, is part of the great recycling, the endless turnover of matter through stars, the cosmic process that has been building and rebuilding worlds and creatures out of the same ancient atoms for over 13 billion years. We're just one turn of the wheel, a beautiful, conscious, fleeting turn, but a turn nonetheless. So keep that with you as we head into the last stretch of this journey. Everything you see up there, the sun, the moon, the planets, the stars, isn't separate from you. It's your family, your origin, your maker, and one day, in the deepest sense, your destination. When the atoms that are briefly arranged into you go back into the great cosmic recycling that made them. The solar system isn't a place you live near, it's a place you're made of, and we've still got more of it left to explore, more quiet violence, more lucky timing, more impossible beauty hiding behind the calm. So stick with me. The best part is always the part you didn't see coming. Now, we've drifted out to Neptune and back. We've fallen into the sun. We've stood on volcanic moons and watched oceans hide under ice. But there are a few corners of the solar system we still haven't poked at, and some of them are the strangest of all. So let's keep going, because the deeper you look at this place, the weirder it refuses to stop being. Let me take you to a planet you basically never think about, the runt, the one closest to the sun, Mercury. Mercury is the smallest planet, the closest to the sun, and most people just file it away as a boring little burnt rock, a gray, cratered ball roasting next to the fire. And yeah, it is roasting. The side facing the sun gets hot enough to melt lead, blasting up to around 430 degrees Celsius. So you'd assume Mercury is just uniformly scorching, an oven of a world, hot everywhere, all the time. Nope. Here's the twist that makes Mercury one of the most extreme worlds there is. Mercury barely has any atmosphere at all. And an atmosphere, like the one Earth has, does this crucial job of moving heat around and holding on to it, like a blanket spreading warmth across the whole planet, keeping the night side from getting too cold. Mercury has no blanket, none. So while the day side is hot enough to melt metal, the night side, with nothing to trap any heat, plunges to around minus 180 degrees Celsius. Let that sink in. The same little planet has a day side that melts lead, and a night side colder than almost anywhere you can imagine. The temperature swing from day to night on Mercury is the most extreme of any planet in the solar system, a span of more than 600 degrees between sunlight and shadow. It's not just a hot planet. It's a planet of brutal, savage extremes. Fire on one face and deep freeze on the other. And here's the part that should genuinely blow your mind. The part that ties Mercury to that moon fact from earlier. On Mercury, the planet closest to the sun, the hottest neighborhood in the solar system, there is ice. Frozen water ice, right there next to the furnace. How is that even possible? Same reason as the moon. Mercury barely tilts on its axis, which means at its poles there are deep craters whose floors never receive any direct sunlight, ever. The sun stays low at the poles, and these crater bottoms are permanently shadowed. And because there's no atmosphere to carry heat into them, those shadowed floors stay astonishingly cold, possibly for billions of years. And in those frozen, eternally dark crater floors, on the planet closest to the sun, water ice has accumulated and survived. Picture that. You've got a world where the surface a few kilometers away is hot enough to melt metal, and tucked into the dark craters at the poles, ice is sitting there, untouched, ancient, perfectly preserved in the shadow. Fire and ice on the same small rock, separated by nothing but a wall of crater. That's the solar system for you. It refuses to be simple. It refuses to be what you'd guess. And there's one more bizarre thing about Mercury before we leave it. Its orbit and its spin are locked together in a strange dance. Mercury rotates on its axis 3 times for every 2 trips it makes around the sun. That's a resonance, just like the ones we talked about. And because of that weird 3-to-2 lock, combined with how fast it whips around the sun on its stretched out orbit, the way the sun appears to move across Mercury's sky is genuinely insane. At certain points in its orbit, if you were standing on the surface, the sun would rise, then actually stop, reverse direction, and dip back down a little, then resume rising again. The sun would do a little loop-the-loop backward in the sky before continuing on its way. A double sunrise on the planet closest to the sun. The cosmos is just showing off at this point. Now let me jump to the biggest planet of them all, the king of the planets, because we've mentioned Jupiter a bunch as the bully squeezing its moons and carving gaps in the asteroid belt, but we haven't really sat with Jupiter itself, and Jupiter deserves it, because Jupiter is absurd. Jupiter is so massive that it's more than twice as massive as all the other planets in the solar system combined. All of them. Saturn, Neptune, Uranus, Earth, everything. Add them all up, and Jupiter still outweighs the lot by more than double. It's a near-miss star, honestly. If Jupiter had gathered up a lot more material when it formed, enough to ignite fusion in its core, our solar system would have had 2 suns. Jupiter is what you get when a would-be star doesn't quite make it. A giant ball of mostly hydrogen and helium, the same stuff stars are made of, that just barely missed becoming one. And the most famous feature of Jupiter is its great red spot. Now, you might remember Neptune's great dark spot from earlier, the storm that came and went. Jupiter's great red spot is the opposite. It's a giant storm, a swirling hurricane of a thing, and it has been raging for centuries. We've been watching it since at least the 1600s, when astronomers first spotted it through early telescopes. So this single storm has been churning for at least 300 or 400 years, possibly much longer. A hurricane that has outlived every human who has ever observed it, by generations. And it is enormous. The Great Red Spot is so big that you could fit the entire Earth inside it, with room to spare. An entire planet, our planet, would just be a marble rolling around inside that one storm. Think about what that means. A single storm, bigger than the Earth, that has been blowing continuously for centuries. There is no storm on Earth that lasts more than a couple of weeks. Our biggest hurricanes burn themselves out in days. But on Jupiter, with no land to break it up and that endless deep atmosphere to feed it, a storm can just keep going and going and going, for lifetimes, for centuries, a permanent feature, a planet-swallowing tempest that's basically immortal by our standards. Although, interestingly, in recent years scientists have noticed the Great Red Spot is slowly shrinking, getting a bit smaller and rounder over the decades. So even this ancient storm might not last forever. We might, just might, be living in the era when the Great Red Spot finally begins to fade after centuries of rage. Lucky timing once more to even get to see it. And here's why Jupiter matters to you, personally, beyond just being a spectacular giant. Jupiter, with its enormous gravity, acts as a kind of cosmic bodyguard for the inner solar system, for Earth. That same gravity that carves gaps in the asteroid belt also catches and deflects a lot of comets and asteroids that come hurtling in from the outer solar system. Jupiter's gravity grabs many of these incoming objects, either flinging them away, swallowing them up, or redirecting them before they can make it to the inner solar system and potentially slam into Earth. We actually watched this happen. In 1994, a comet called Shoemaker-Levy 9 broke apart and crashed directly into Jupiter, and we watched the impacts, which left dark scars in Jupiter's atmosphere bigger than the Earth. That comet could have, in another scenario, been headed somewhere else. Jupiter took the hit, so the king of the planets has, over billions of years, very likely shielded Earth from countless impacts, soaking up or deflecting threats that might otherwise have caused mass extinctions here. It's not a perfect shield, and sometimes its gravity flings things toward us too. It's complicated, but on balance, that giant out there has probably helped keep Earth safe enough, long enough, for complex life to develop and survive. So the next time you think about Jupiter, that distant striped giant, give it a little nod. It may be part of the reason you're here at all. Now, let me come back to Earth, our own planet, because after this whole tour of extremes and violence and bizarre worlds, I want you to really appreciate just how absurdly, improbably perfect our own little rock is. Because we've seen the alternatives now. We've seen Venus, the same size as Earth, turned into a crushing acid furnace. We've seen Mars, once possibly wet and warm, now a frozen desert with an atmosphere blown away. We've seen the airless extremes of Mercury and the Moon, and against all that, Earth sits in this one narrow sweet spot, this Goldilocks zone, where everything is just right. Let me lay out just how many things had to line up. Earth orbits the Sun at exactly the right distance, not too hot, not too cold, the one band where water can exist as a liquid on the surface. A little closer, like Venus, and our oceans would boil away into a runaway greenhouse. A little farther, like Mars, and they'd freeze solid. We're right in the middle of the habitable zone, the thin ring around the sun where life as we know it is even possible. And it's not just distance. Earth is exactly the right size, big enough that its gravity can hold on to a thick protective atmosphere, the air you breathe, but not so big that it crushed itself into a gas giant. We've got that molten iron core generating the magnetic field that shields us from the sun's deadly radiation, the invisible bubble we talked about. We've got plate tectonics, which recycles carbon and regulates our climate over long timescales, acting like a planetary thermostat. We've got the moon, large enough to stabilize Earth's tilt, keeping our seasons steady and predictable, instead of letting the planet wobble chaotically over time, which would wreak havoc on any climate trying to support life. Every single one of those things had to be in place. The right distance, the right size, the liquid water, the atmosphere, the magnetic field, the tectonics, the stabilizing moon, the protective giant planets out beyond us soaking up impacts. Pull any one of those away, and Earth might be lifeless. It's like winning a cosmic lottery a dozen times in a row, and the result is this one blue, wet, green, living world, this single oasis of life that we know know of, hanging in the vast, cold, mostly empty, mostly hostile expanse of the solar system. Everywhere else we've looked is either too hot, too cold, too crushing, too poisonous, too airless, too dead. And then there's Earth, teeming with life, with oceans and forests and creatures and us, the one place that got everything right. And here's the thought I really want to land. From space, Earth is tiny. There's a famous photograph taken by the Voyager 1 spacecraft in 1990 as it was leaving the solar system. The scientists turned the camera around to take one last look back home, and in that picture, Earth shows up as a single point of light, less than a pixel, a tiny pale blue dot suspended in a beam of sunlight, lost in the immense darkness of space. The astronomer Carl Sagan described it beautifully. That dot, he said, is here. That's home. That's us. Everyone you've ever known, everyone who ever lived, every king and farmer and child, every war, every love story, every triumph and tragedy in all of human history, all of it happened on that one tiny pixel, that pale blue dot, floating alone in the cosmic dark. Everything you've ever cared about, everything that has ever happened to anyone, the whole of human experience, all of it, on that one small point of light. And that perspective, weirdly, isn't depressing. I think it's the opposite, because when you really understand how rare, how fragile, how staggeringly improbable this living world is, set against the violent, empty vastness of everything around it, you start to see how precious it actually is. We are, as far as we know right now, the only place where the universe woke up and started looking at itself, the only spot where star ash organized itself into creatures that can wonder and love and build telescopes and send robots to land on comets and fly past Pluto. That's not nothing. That might be the most important thing happening anywhere within reach. And it's all on that one little dot, the one we share, the one we'd better take care of. Because in every direction we've looked, there's no backup, no second oasis waiting, nothing but the cold and the dark and the quiet violence we've spent all this time exploring. So let me pull the whole journey together now, because we've come an enormous distance. We started way out at Neptune, with supersonic winds screaming through the frozen dark, faster than sound, in a place that should be dead quiet. We found diamonds raining down through the crushed insides of the ice giants, treasure forged out of methane under unimaginable pressure. We met Venus, the backward world where a day outlasts a year and the sun rises in the west. We watched Saturn's rings, that perfect crown, slowly raining away into the planet, younger than the dinosaurs and fading before our eyes. We relived the moment a human being found Neptune with nothing but a pencil and the laws of gravity, summoning a planet out of pure mathematics. We stood at the base of Olympus Mons, a mountain so vast it would bury an entire state and pokes out the top of Mars's atmosphere. And we felt the ancient sunlight on our skin, energy born in the sun's core before human history began, that spent hundreds of thousands of years just escaping the star before crossing the dark to touch your face in 8 minutes. And then we kept going. We met Io, the tortured little moon squeezed molten by gravity, the most volcanic place there is, bleeding its insides into a ring of plasma around Jupiter. We found Europa, with its hidden global ocean under the ice, maybe holding life, maybe holding the answer to whether we're alone. We discovered water lurking in the dark shadows of the moon, and even on Mercury, fire and ice on the same scorched rock. We learned that comets are time capsules and delivery trucks, possibly carrying the very water and ingredients of life to the young Earth. We busted the myth of the crowded asteroid belt and saw the staggering emptiness that truly defines this place. We made peace with Pluto, the demoted dwarf that turned out to have ice mountains and nitrogen glaciers and a giant heart on its face, and we glimpsed the unimaginable Oort cloud at the very edge. So far, our fastest machines need tens of thousands of years to cross it. And then we fell into the heart of it all. The sun, that gravity-caged nuclear explosion, holding 99.8% of everything, burning 4 million tons of itself into light every single second. We watched its violence reach out and paint the aurora across our skies, deflected by Earth's invisible magnetic shield. We heard the mathematical music of orbital resonance, keeping the whole system in delicate balance. And we felt the moon's gravity lifting the sea at our feet in the tides, slowly stretching our days and drifting away. And we learned the deepest truth of all, that you are made of stardust, your every atom forged in dead stars and scattered across the galaxy long before the sun was born. The universe, made of recycled stars, looking at itself through your eyes, and through every single piece of it, that one theme kept rising to the surface, over and over: quiet violence. A solar system that looks calm and peaceful and serene from your back garden, but is actually running on the most extreme forces imaginable. Ancient catastrophes, crushing pressures, screaming winds, permanent explosions, gravitational vices, and delicate balances that took billions of years of chaos to settle into the fragile peace we enjoy today. The stillness you feel when you look up is real, but it's a stillness laid over staggering depth, the way a calm sea hides unimaginable forces underneath. And the other theme, the one I hope you really felt by now: lucky timing. So much of what makes this place beautiful is fleeting, a window, a phase, the sun in its calm middle age, the one stretch where it shines steadily enough for life. Saturn's rings, here for just this moment in cosmic history. The moon at exactly the right distance for perfect eclipses, drifting away even now. The great red spot, slowly shrinking after centuries. The rings raining down, the moon receding, the sun aging, all of it temporary, all of it a passing show. And we, somehow, exist right in the middle of all those windows at once, with eyes to see them and minds to understand them. That's not just lucky. It borders on miraculous. So here's what I want you to take away from all of this. The thing I hope sticks with you long after you've forgotten the exact numbers and names. The solar system isn't some distant abstract thing you learned about in school, a diagram with neat little circles. It's the place you're made of. It's your origin and your home, and in the deepest sense, your family. The same starfire that warms your skin is the kind that forged the atoms in your bones. The same gravity that holds the planets in their orbits lifts the tide at the beach and keeps you pinned to the ground. The same quiet violence that rages across Neptune and Io and the sun is the engine that, over billions of years, built this one improbable oasis where you get to be alive and awake and aware. You're not a spectator looking at the cosmos from the outside. You're a part of it. A small, warm, conscious, fleeting part, but a real one. The part that's paying attention. And that, I think, is the most relaxing fact of all, in its own strange way. Not relaxing like a quiet nap, but relaxing like the deep calm that comes from finally seeing where you fit. You are a brief arrangement of ancient stardust on a tiny blue dot in a vast and violent and beautiful solar system, given the rare gift of being able to look up and understand a little piece of it. That's an extraordinary thing to be. So the next time you step outside and you feel that 8-minute-old sunlight on your face, and you look up at the moon pulling the tides and the planets wheeling in their ancient resonant dance, and the stars that forged you scattered across the dark, I hope you feel it differently now. I hope you feel a little less small and a little more connected, because it's all out there, running its quiet, patient, magnificent machinery, the same as it has for 4.5 billion years. And you're here, right now, in the one flickering moment when something can finally notice. So go on, step outside, look up. It's your sky, your system, your story, and it's been waiting 4.5 billion years for somebody to pay attention. That somebody somebody tonight is you. That's the drift. That's the solar system. Calm on the surface, chaos all the way down, and somehow more beautiful for it. Thanks for falling through it with me. Now go look up and don't stop wondering.